Good afternoon. It's an honor to be here to present my work. And it's a mitigation for kernel TOC TOU vulnerabilities. And I'm Mingbo Zhang. I'm a student from Rutgers University. And my advisor is Saman Zonouz. TOC TOU stands for time of check to time of use. I think maybe you've heard that. And it's not a new vulnerability. It exists probably 2 or 3 decades. And it has many different forms. And the one we're going to talk about in this presentation is the one that happened in operating system kernels. And sometimes kernel TOC, TOU, also known as double fetches, sometimes risk conditions. And here are the list, some of the CVEs in recent years, just to show that's a real thing, kind of a real threat. So here's a piece of kernel code which has a kernel TOC, TOU vulnerabilities. Like the kernel function take parameters from user, and the parameters may contain other pointers that directly point to user space. So when the function runs, it may reference this pointer and try to get data from user space directly. Let's say it gets data FF for the first time. And it uses this data, try to allocate a buffer. But meanwhile, there could be an attacker that uses other user mode threads, keep changing the data. For example, we change FF to 8FF. So you can see it's much larger. But the kernel function doesn't know that. So the kernel function, when the second time it references the pointer and gets data, it gets a much larger value. And it uses this value to copy the buffer. And now we can see there will be a buffer overflow. And that's basically how kernel TOC TOU works. And we think about why it happens. I think it's because kernel gets data directly from user memory twice. And user memory is a shared resource. So there's no mechanism. So when other thread changing those memories, there's no mechanism to inform the kernel or other user thread when that happens. And the right way to do it, especially for Windows kernel, is to capture the value, means copy the value and make its own kernel copy. So no matter how many kernel function need to use this value, it only uses its own kernel copy, so it won't be changed by other threads. But unfortunately, not all codes do that. Some code may forget to do that. And so that's why we try to come with a mitigation. And our idea is very simple. Basically, anything kernel touches should stay the same. So let's say there's one user thread initiate a syscall with parameters passed in. And those parameters contain other pointers. So when the kernel reference those pointers and access user page, and we think this page should be protected, and it should not allow other user threads to overwrite it. But the problem is, how do we know when the kernel access user memory? There may be some solutions. Like for example, people use date watch points. That's hardware breakpointer to set little traps in the memory space. So whenever the kernel triggers those traps, you get a page fault, and the kernel can know. Or there may be, you can use transactional hardware transactional memory. Use that, you can keep data integrity. But I think both hardware transactional memory and data watch points are quite limited hardware resource. For example, you cannot put the whole syscall into one giant transactional operation. And for the data watch points, basically you only have 4 of them for each core. So we noticed there's a hardware feature from Intel. It's called Supervisor Mode Access Prevention. And this feature does exactly what we need. So basically, when kernel access user pages, it triggers page faults. And so we know things happens. And to enable it, it's also very easy, very simple. You just need to set the SMAP bit in CR4 registers. And you also can disable this feature temporarily by setting AC bit in E-flag registers. This feature already been adopted in Linux kernel. So whenever Linux kernel want to get access to user mode memory, you need to go through those two gateway functions. Those are copy to user and copy from user. And within those two functions, SMAP is temporarily disabled. So other than that, if the kernel tries to access user memory, it will trigger page faults. In this presentation, I call it SMAP exception, but actually SMAP exception is one type of page fault. So even though Linux adopt SMAP, doesn't mean it don't have kernel TOC, TOU vulnerabilities, because programmers may, for example, use copy from user twice for the same variable. So this problem still exists in Linux kernel. But for us, we want to leverage this feature differently. So when the kernel memory, the kernel code accesses user memory, it will trigger page faults. And we handle the page faults. Instead of crashing the kernel, we want to put the page into kernel space by setting a user supervisor bit in the corresponding PT tables, PT entry. So doing that, it has two benefits. One is this page is protected from all other user threads because in the kernel space now, so no other user thread can override a kernel page. And the second is, by doing that, we can satisfy the current, this SMAP page fault. So when we re-execute the faulting instruction, it won't be triggered again because it's no longer a kernel code it's no longer a kernel code access user memory anymore. So what if other threads really need to read the same page? And what we do is really simple. We just put this page back again, but with read-only permit. Because is user thread access a kernel page this time, it will also trigger a page fault, and we handle that page fault, and we can do this. So during the whole time, from the first time a syscall references the user page, and until the current syscall ends, the page is being protected either by putting into kernel space or putting in user space with a read-only permit. So the whole time we protect this page from other thread overwrite. And until now, the implementation is very simple. We just need to hook page fault handler, and most work are done there. And we also need to hook one more Windows internal function, that's ki syscall exit, just to let us know when the syscall ends. So in page fault handler, we only handle the exceptions that's related to SMAP. All others we just pass through OS kernel. And in the handler, we can get some useful information from stack. Like we can get page fault error code, and we get some registered image, and we can get current page directory base from CR3. That tells us who is the current process. And we get the faulting virtual address from CR2. But the problem is, when we enable this feature, there will be a huge amount of exceptions. Because SMAP is a system-wide feature. When you enable it, you enable it for the whole system, every process. And Windows kernel didn't adopt this feature yet. So it gets user data, you use its own way that directly gets data. So every time it does that, it triggers page faults. And a lot of system code has user parameters. And perhaps there's some reason behind this is there may be some kernel modules, such as Win32K, I think they may store some data in the user memory, in the user part. So that's why there's so many exceptions. And what we have is Windows Debugger. And Windows Debugger, WinDBG is a software debugger. So when I use Windows Debugger to debug a low-level system mechanism, such as page faults, sometimes it's not very convenient because I think the debugger itself may further trigger page faults. So that easily gets us into a dead loop. So we need to heavily reduce exceptions to let us be able to debug the whole thing. And we want to debug one process at a time, not the whole system altogether. So we think probably we can use virtualizations to confine this feature within one or several processes. So we implement a very simple hypervisor, and basically it loaded as a Windows kernel driver, and it doesn't emulate any devices. So when it runs, it just lifts the whole operating system up into guest mode, and itself can intercept all the VM exit events underneath as the hypervisor with a more higher privilege. And our goal is we want only set SMAP bit when the CPU runs on the target process. And here's an example. We monitor process context switch events. For us, that's move a general register to CR3 register. So when that happens, it will cause VM exit, and it will exit to the hypervisor. And the hypervisor, we set SMAP bit to 1. And when hypervisor go back to VM again, the data will be flashed back to the real processor. And so for the target process, it feels that SMAP is already been enabled. And when the target process switch out, we do the opposite thing. We just set SMAP bit to 0 in those related fields of VMCS, that's virtual machine control structure, and the same when go back to VM, flash data back. So for other process, they think SMAP is not enabled. But by doing this, we can allow SMAP page fault only happen inside the target process. And we need to try to solve this thing. So we protected the page already, but what if some user thread really want to write this protected page? Because it could be global variables in that page, or we know threads, they share heap memories. So we think about how to solve this problem, solve the write conflict. So at the beginning, we think we probably can implement a thread-level copy-on-write mechanism. So when other threads try to access this protected page, we split page tables and give them actual physical page. But it has a problem because we need to figure out when we are going to merge those two physical pages back. And we have to decide which copy we're going to use. So eventually, we give up that idea, and we come up with a much easier idea. That is, when other user threads try to write the protected page, we simply let other user threads wait there until the current syscall ends and done with the page. What that means, we have to let a thread looping inside the page fault handler. So at first, that doesn't sound very nice because it's page fault handler. We should do things quick and get out. But since I read through the manual, it seems quite doable because interrupt describer table contains two types of things. One is interrupt, and the other is exception. And interrupt basically caused by external devices, and exception caused by the processor itself. And page fault is an exception. So when interrupt happens, the OS will bring its priority to a very high level. So for Windows kernel, that's IRQL. So in the interrupt situation, we need to do things quick and get out. But for exception, the IRQL depends on the context. So in our case, it's the user thread triggers this page fault. So the IRQL will be at passive level. And we know at passive level, we can call a lot of Windows kernel APIs. So we choose this KE delay execute thread. That's a kernel version sleep function. And we can let the thread sleep in the page fault handler and let OS rescheduling. So now that sounds not too horrible. And we see this picture again. So the page is protected. And when the user thread tries to read this page, in the page fault handler, it will sleep for several milliseconds, wake up, and check permit. If the kernel syscall done with the page and let the page go, then the thread can re-execute the faulting instruction and do its thing. And if not, it will go back to sleep and try several times. And if no luck at all, we just return access violation to terminate the thread in order to avoid any deadlock. Here are some implementation details I think I should mention here, because our mitigation based on put the page into kernel and user space back and forth, and basically what we do is modify its corresponding page table entry. So we do that, we need to consider how to do it in a multiple processor system, and we also need to invalidate corresponding TLP entries, because every core has its own TLB. And we do it on local core, we just issue an instruction. But we also need to send an inter-processor interrupt to all other cores. But in this case, we took a shortcut. We just call Windows internal function, that's ke/single-tb, to do that for us, and it works. Well, actually, before this presentation, I think I probably should check the manual more and try to implement the whole API thing. But I just spent too much time preparing these slides. And there's another thing. We need to set interrupt flag in the page fault handler, because this is a very interesting and confusing concept. Page fault is an exception, but it's also implemented through an interrupt gate. And we know for Intel, there are interrupt gate, trap gate, and task gate, call gate. But basically, interrupt gate means when page fault happens, the processor will automatically clear the interrupt enable flag in the eFlags register and set it back when the page fault returns. But we think the reason we need to do that is because our page fault handler may further trigger more page faults. Like we walk us through the page tables, it may trigger more page faults. And actually, I didn't know this before. It's just after so many crashing, the system and debugger freeze altogether, I just ran out of option. And I think the project started already half year. It's already too late to quit. So I just randomly try things. And after I set this flag, it solves a lot of problem. And then I know I need to set this quick. And right after, I get the faulting virtual address from CR2 register. And here's the evaluation. Our test bed is a Intel Core i5 6th generation processor with H110 chipset. And we use this quite classic CVE 2008-2252 vulnerability. And we write a little simple POC code, which just trigger the vulnerability and crash the system. There's no payload. So that's vulnerable code. There are 3 places in the code access user page. Actually, the circle 2 and circle 3 place are the real double fetches, as I introduced in the C code earlier. But circle 1, the first place, is vulnerable code, the first time access user page. So when it accesses a page, trigger page faults, and that's where our mitigation kicks in. We put the page into kernel space. So in our POC code, we have an attacking thread looping there, try to modify the data, and it will be blocked in the page fault handler. And until the current syscall ends and damages the page. So at this time, the attacking thread can run, but it's already too late. We already protect that part of vulnerable code. And here's the evaluation, performance overhead. We are quite lucky to be able to run our mitigations on several applications. And it's quite difficult to precisely measure the performance overhead. So for example, for the web server, we just run the Apache tool to send multiple requests and to count the time. And the performance overhead is reasonable, among 4 or 5%. And I think it's based on how often you call syscall. Okay, here's our side project. I think I skipped the slides. We want to use the same hardware feature, this time not for mitigation, but try to find more vulnerabilities of the same kind. So this project is inspired by BoxPong, identifying and exploring Windows kernel race condition via memory access patterns. Basically, this project uses Box, a fully software-emulated hypervisor, to monitoring all the kernel, all the memory accesses. But the problem is Box is very slow. It's a fully software-emulated hypervisor. It doesn't have any hardware-assisted virtualization, and it interprets each instruction it executes, so it's very slow. We just want to do it better and more fast, so maybe we can run more deep into the application. So we want to use SMAP just for monitoring, and it will be much easier. When the kernel triggers SMAP page faults, we just record some information and let the kernel go. But still, this also have a problem. So once SMAP triggered, it's already too late to disable it by setting AC bit in eFlags. So for us, we have to do the same, the old trick. We have to put the page into kernel space and satisfy the current page fault. And we also want to release this page really soon because we want to record all the accesses. So we think we can use SMAP with single-step trap. So we can gain back control right after the next instruction. But the problem is, as what debugger do, you set trap flag, and you also need to set resume flag. And because you don't want single-step trap right triggered inside your handler. But the problem is, the resume flag only works in a debugger context handler. So for us, our work is done in page fault handler. So this resume flag doesn't work. So we have to do it in a very harder way. We have to set breakpoints manually. So in page fault handler, we just set a breakpoint that's a byte CC into the next instruction. So when that triggers, our hypervisor will intercept the breakpoint trap event And we will write back the original byte and release the protected page, re-execute the faulty instruction, and let the kernel go again. And that works. And the memory access pattern we are looking for is same user mode virtual address that being accessed more than once has to be within one syscall, has to be done by the same thread. And we get some result. There are two types of things. We identify some places in the kernel module that it accesses user mode memory without a track cache block. So that's just a minor issue, but that can lead to local DOS attacks. And we also find some double fetches. Here's the part of the log. You can see there are those are same process, same thread, EIP not too far away, access same virtual address. And here's an example. Within one kernel function, two places access the same virtual address. And here's an example. Two kernel functions access system virtual address, but those two kernel functions are very close in the code stack. It's the first function called the second function. So I think this case could be a little bit more difficult for the static analyze tools to find out. But those are just double fetch bugs. I think it's not a vulnerability yet. Probably a lot of the double fetches are benign, but some could be turned into a vulnerability. And I think that's our future work. So future work, we want to further look into those double fetches, and because I need more knowledge about Windows kernel graphic interface, how it works, and how the data structure organized. And we also want to, because this mitigation, also this fuzzing tool, are quite operating system independent. Not exactly, but kind of. So we want to move our mitigation and this fuzzing tool to Linux kernels and Mac OS, try to find more vulnerabilities. And currently we only implement a 32-bit, so probably we need to implement a 64-bit version. Okay, finally, conclusions. So we provide a real-time mitigation for kernel TOC TOU vulnerability, and the performance overhead is not too bad. And we also provide a tool that monitoring kernel to user memory access patterns. That's it. Questions? Thank you.
Hi. So for the mitigation, how do you protect between threads that write to some memory location using the kernel? So you can issue a syscall that will write to your address that you're trying to protect. And currently, it looks like you have two modes, user and kernel.
Oh, yeah. You mean, what if the kernel try to access protected page, right?
Yes, right to that.
Yeah, because the page, when we first time protected it, the page will be put into kernel space. So when other kernel threads try to access it, that's fine, because it's no longer because kernel code, we trust it. You are in kernel code that won't trigger vulnerabilities. So that's not in...
But the other thread might be controlled by a user mode that reads, say, from a file, especially to that location. So instead of writing directly to that location, it makes the kernel write to that location.
You mean this user thread call some syscall or make some operation that let the kernel thread change that page?
Yes.
Right? Well, I never think about that. Yeah, that's a valid question. Yeah, I think I should consider about more. Yeah, I would think about it, and yeah, in that case, mitigation doesn't work, right? Yeah, that's valid
the
question.
detection part is brilliant, but
Thanks for the point taken.
Yeah.
I will further think about it.
I had the exact same question.
Well, looks like that's a very authentic question. I should work on that.
Any more questions? No? Great. Thanks very much, Mingbo.
Oh, thank you.